Hello, welcome to DebConf 23. NIIBE-san is a cryptographic expert and is a GNU PG developer. He's made hardware, free hardware like the GNU key, and is going to talk about random generator. Thank you so much.
Hello. Today my talk is about my own collection of PLL-based true random number generator using FPGA. I do this talk together with my wife, Hitoe. And you will see our presentation, our demonstration today. And here is the content. I explain why we need true number generator. Perhaps my talk would be too technical, but you can enjoy that. I hope so. And I explain PLL-based TRNG on FPGA briefly. And we do that demonstration so that you can understand or remember how true random number generator works on FPGA. And then I explain a collection of PLL-based TRNG on FPGA. That's my work. And I do that. I show you an example, concrete example using the board named Tech0117. That's made in Germany using Chinese FPGA, Gowin. And then I run demonstration, visualize random output. That's my talk. And let's see. And in this slide, I explain why we need true random number generator. And my daily work is a cryptographic tool called GNU PG. And we need, for cryptography, it depends on random number. And likewise, fair computer games need true random number generator. Or computer slot machine also require true random number generator. Because when someone, suppose that someone controls random number generation in a computer or in a system, then someone can know beforehand the result. So we need something which no one controls its sequence. And in other words, no one can know until actually see the sequence. That's the things for true random number generator. And because true random number generator feature is so common on computers, these days we have a RD-RAND instruction on Intel architecture, or TRNG module is so common, even in a very small microcontroller. So I guess that when you have a smartphone, you have a multiple true random number generator implementations on your hand, I guess. And in the historically around DebConf, we had those demonstration or talk in DebConf. It was around 2015, and in Germany, someone demonstrate OneRNG. Or next year, ChaosKey talk was available. And also, I explained NeuG, my own implementation on MCU in DebConf in Germany. And let's consider this situation. If true random number generator module were actually controlled by someone in a vendor or someone as a service engineer, then that person would be possible to know your information of your key materials when the true random number generator module is used when you generate your key. So suppose that it's actually pseudo RNG instead of true random number generator with a seed, and that seed is controlled by a vendor or a service engineer. In that case, you lost your security at all. So point is that none except the if it is a pseudo random number generator with a seed, none may be possible to claim that it is the sequence is actually controlled, because the output itself just looks like a random number sequence. No one can distinguish the sequence if it is controlled or not. So thus, transparency of the module random number generator matters. It is just like a free software, like a Debian operating system. Transparency matters here. So, in this presentation, I'd like to say that we need more TRNG, especially do-it-yourself version of TRNG, or more transparent to random number generator implementation is needed. More is needed. Last year, I thought around the TRNG technology again, as I did in 2015 for do-it-yourself TRNG. And these constraints, easier to implement cost-wise and technology-wise. And it should be patent-free, patent royalty-free. And it should have better reproducibility. Not only a single instant in a laboratory, but everyone can reproduce that module. And it should be buildable with commodity parts. Something like you can buy Mother or DigiKey, or it should be buildable with free tool, as in freedom. I mean that you should not have dependency on proprietary software to build those tools, those TRNG, because if we need some proprietary tool to build TRNG, it means that less transparency. Someone with the build tool would control something. So free software and free tool is very much important to build such a, even for those hardware modules. And this is my conclusion in 2022. PLL-based TRNG can be built fulfilling those constraints. Easier, free, reproducible and commodity and using a free tool. And it was first published by Victor Fischer and Milos Dultalovsky. And so it's quite old technology, actually. It's like more than 20 years ago. So if patent would exist, patent were existed, it should be expired already. And now we have a good free tool chain for FPGA, and it can be built more transparently than ever, because we now have a free software tool chain for FPGA. And so practical USB device can be built with FPGA easily using an FPGA chip plus USB serial tape. And this is just a hardware part explaining a phase-locked loop. Phase-locked loop is quite a common technology in digital circuit. And usually FPGA chip comes with PLL, multiple PLL modules. So it's common technology. The functionality is that generate a clock output from input reference clock. Example is that input is 100 megahertz and the output is 425 megahertz, just like that. And the PLL-based TRNG structure is like that. We have a two input, 2 generators, and a sampler, and a post-processing unit, and it outputs random bits. Pretty simple structure. And basically, it captured the jitter for randomness. Jitter of clock. Yes. And one clock is sampled by another clock. That's the structure. And conditioning can be done by accumulating many bits with XOR, resulting a bit. This is a concrete example. Today's demonstration, I use a Tech 0117 board, which has Gowin GW1NR-9 FPGA chip, and it has a 100 megahertz crystal and 2 PLLs. I configure it for 425 megahertz and another 192 megahertz. And as I said, many bits. How many? Like 192 bits to get a single bit. So many bits is needed to get even a single bit of randomness. And using serial output. That's a concrete example. So here comes our demonstration, so that you can remember the philosophy of the PLL-based true RNG. Here we have 2 persons, Japanese beautiful lady and me. And one person is doing exercise so-called Hindu squat. In Japan, we call it Hindu squat, but I don't know the Indian people knows that. It's like exercise. This represents one signal, one generator, low and high, low and high. And another person is represent another signal, another clock source. She does look back and look back. It represents 0 and 1, 0 and 1. So the PLL-based TRNG runs like that. Let's do that. I do that, my own exercise, 0 and 1, 0 and 1. And when she look back, if it is 1, she changed the state. 1, 0, 0, 1. If it is 0, when she look back, she doesn't change his bit, her bit. And she have to do that 192 times to get a single bit. So, you know, I'm a bit older than ever. So it's impossible for me doing continue this 192 times. So this is just for explanation. So I finish my exercise now. So I hope you remember the principle of PLL-based TRNG. Yes, thank you, Hitoe. And so Gomti is a collection of such a PLL-based true random number generator. There are multiple collections, multiple implementations, or multiple bit streams. And the target board is ICE40, Gowin, 2 variants of Gowin FPGA, and here is the target board. It costs like $30 to $50. So it's a kind of commodity board. And this is again the TRNG structure. And we can imagine that it goes like that. Generator 1 says 1 month flashes, and generator 2 says another month pleasure. And this is how I name the project Gomti. Because I decided last year that I should have a presentation in India, Kochi, India. So it should, a project name should be something like India. And so I take this Gomti as an acronym to remember the first part of this conversation. 1 month flashes, and it is coincidence that the Debian logo looks like just looks like Gomti chakra. So here is the repository of Gomti URL at the source hub. And Gomti repository includes Verilog source code and the parameter for TRNG and generated bitstream and helper script for development. And you need those tools, those free tools to build your own TRNG. And the Debian book and testing is best for Gomti. And this is how to develop TRNG with Gomti. And please clone the repo and fork it and select FPGA and configuration and build with YOSYS plus next PNR. And you can evaluate the sequence using the SP890B entropy assessment. And this is an example, running example of the board. And lastly, I do demonstration. This is a running stream, random bits generated through through random number generator. Yes. I'm afraid that this is not good for, this demonstration is not good for video team. I'm afraid. Anyway. So, question? Yes, please.
So first of all, it's really good that you're seeing that you're looking at the NIST standards for verifying and validating your random output. So, Bonzo, great. How are you stopping external bias? So how are you preventing external environmental conditions biasing your two clocks in a particular way? So for example, if I were to heat your primary oscillator or your secondary oscillator, I could sway the sequence. I'm not going to clear randomness entirely, but I am going to be able to push it into a higher probability that it's going to give me a 1 or a 0. How are you preventing that?
That's a very good question. And those kind of attack is very difficult for through random number generator. And in my opinion, we need some protector for example, if the attack is by heat, we need some protection around the TRNG implementation. And if it is by electric wave, we should have some protection against electric wave. Those can be done, but mechanical, physical disturbance would be also possible. And so there are various kind of attack, environmental attack to FPGA or implementation of TRNG. That's true. That's a very good point.
So you've looked at it using this as your entropy source. You've looked at a method of validation for NIST. Protection against that is left as an exercise to the reader. Yet we can all sort of scope everything within limits, and we can monitor that, so we've got an idea if we are exceeding normal operating conditions, so we can detect a potential attacker.
Yes. So
how do we increase the bit rate of our output? Because as you saw that, as you've demonstrated, you're looking at a 0.5 megahertz signal coming in to give you a very low amount of entropy coming out. How do you? Where is the limit with today's FPGAs to the maximum bit rate we can get out?
Basically, it depends on the actual configuration of the implementation of the board and how we configure in this structure. I just explained the first phase of the random number generator, but usually it comes with a testing module, so that we need to detect malfunction of the random number generator. So it should be always monitored by another component of the device. And when we detect some invalid situation of this module, such a monitor module should be detect the malfunction of this functionality. Yes, that's usually how we compose the real device for TRNG. This is only the first part of the TRNG implementation.
The second part of the question, where I was asking, what is the bandwidth limit? How fast can we get out?
It depends on the parameters, and it depends on the FPGA performance. And usually an example, this is not a good example, and it's like a 1 megahertz output. It is possible for daily commodity FPGA. For more bandwidth, we need more better FPGA or some special PLL modules. Those frequency is these days common. 400 megahertz or 200 megahertz is common in circuit, in digital circuit these days. And with those commodity frequency, we get this kind of bandwidth for output. And I think that would be enough for usual use case. It depends.
Thank you very much. We are sorry we are out of time, and we thank you so much. I guess people can ask you a question on outside of this talk. Thank you very much.
Thank you.